Hi everyone. I'm Praneeth from the University of Bonn. I'd like to thank the organizers for making DRP this year accessible to people around the world. Also to Ersin, who has worked a lot for this particular presentation. Now I leave it to him to explain to you something about category theory and its connections to logic. Yeah, this presentation will be about the category theory, a categorical logic, and introduction to that picture. First, we will talk about what the category is. First, we will talk about category theoretical concepts, basic concepts, and then we will talk about what at first order language is and what is categorical logic is about. And then there are two special concepts called internal logic and a generic model. First, let's start with category theory. Category theory is a theory for studying abstract things and the relations between them. It's special because it emphasizes the relationships between things. So it's a structural philosophy kind of thing. Instead of concrete representations, you think about connections between them. It's also an independent foundation for mathematics and closely related to computation, type theory, and logic. Formally, a category is just a bunch of objects and morphisms between them. You can think of morphisms as arrows or functions or any process from an object to another. And you can compose morphisms together. For example, you can compose F and G because their domains and codomains are compatible. And this composition is associative, and you have identity morphisms for the composition operation. Basically, you can visualize a category as a directed graph, and vertices are objects and paths are morphisms. And we have a lot of examples of categories. For example, category of sets and functions between them, topological spaces and continuous functions between them, vector spaces and linear functions, groups and group homomorphisms. These are all set-based categories. Underlying structure is always set. But I mean, if you have any poset, then you can see its elements as objects and expressions like x is less than or equal to y as morphisms. And this is not a set-based category. And we have special types of morphisms we all are familiar with. For example, isomorphisms, monomorphisms, epimorphisms. Monomorphisms are like injective kind of things, and epimorphisms are like surjective kind of things. And we have, for example, a category is a mathematical structure, and the structure preserving maps between categories are called functors. And they preserve composition, identity, and objects. So they send objects to objects, morphisms to morphisms, and respect composition and identities. And as an example, for example, a large class of examples are called forgetful functors from groups to sets. You just send a group to its underlying sets, or abelian group to its, and you just forget that structure is abelian. Or you can construct three groups from sets, or you can take the abelization of a group, and these are all functors. And as a recursive manner, these functors and categories form also a category of all categories. And all is in quotation marks because there are some foundational issues, but this category is called cat. And there are some special types of functors. These are all called adjoint functors. They're important because, for example, there's a slogan by Saunders McLean that adjoints are everywhere. Whenever you have two processes in opposite direction, there's a pretty good chance that these are actually adjoint functors together. And you can, I mean, the definition is not important for this presentation, but you can think of adjoint functor as a best possible inverse for a non-invertible functor, for example. And examples is that the forgetful functor from group to set and free group functor from set to group are, for example, adjoint functors. And trivial topology, discrete topology, and forgetful topology are all functors. They arise everywhere, basically. And there is another important concept in category theory. I mean, first of all, category theory gives us a very powerful diagrammatic language to talk about things. For example, a lot of theorems goes like there is such things and the following diagram commutes. And we can also do operations with these diagrams. For example, limits and colimits are two such operations. First of all, a diagram is, it's just a collection of vertices and edges. Edges are morphisms and vertices are objects. And we say that the diagram commutes if all paths from one vertex to the other are amounts to the same morphism. For this graph, it amounts to F equals ME. And then there are special common diagrams. These are called product diagrams, and this is called a pullback diagram. This is called an equalizer diagram. I mean, this empty diagram is also very famous. And we will explain the concept of a limit from the pullback diagram. And we take our pullback diagram. A cone over a diagram is just an object together with morphisms such that this resulting diagram commutes. And then sometimes there is an optimal cone, in the sense that for any other cone, we can find a unique morphism in this direction. And this optimal cone is called the limit of the diagram. And colimits can be defined in entirely analogous manner. In category theory, when we say co, it usually means just reverse the direction of arrows. For example, this is the push-out diagram, the co of pullback diagram. And this explains the limit, co-limit of this diagram. Sometimes seeing how this turns out in these limits are how can be computed in sets adds a lot to our intuition. And products corresponds to Cartesian products, and coproducts are disjoint unions, and equalizers they are just the agreement subset of a two function, and pullbacks are just preimages in the category of set. And in set, we have also a very important notion called a subset, and subsets are actually can be identified with injective maps. We say that two injective maps are equivalent if they have the same image. So a subset is actually an equivalence class of injective maps. And I mean, when we define a concept in entirely morphisms, we generally have a generalization of this concept to abstract categories, and we do that here as well. We define a sub-object as an equivalence class of morphisms. And for instance, sub-object of X is equivalence class of morphisms into X, and they are equivalent if they are connected by an isomorphism like that. And we write it as a sub-X, a collection of all sub-objects. And we can even define an order for sub-objects. So if you relax that this sigma is an isomorphism and just take any morphism, then we write that M is less than N, and this gives us a partial order on the sub-object structure of X. And even more, the sub-object structure of X is a meet similar, so finite meets exist, and proving this is very easy, just core. Of course, if C has pullbacks, then the meets exist. So if you just compute the pullback of two sub-objects, you get the meet of them. You can think of it as an intersection. And then another important concept related to subset is preimages. And if you have a function in set, you can compute its preimage. And in the limit slide, we saw that the pullback diagrams are actually related to preimages in the category of sets. So to define a preimage in the abstract categories, we will use pullback diagrams. For example, and this is the situation for sets, but we generalize the same thing for general categories. So if you have a sub-object M, we define the preimage of M through F as the result of this pullback diagram. And this is actually a well-defined definition. I mean, we should check that pre-image of a mono is also a mono, but this turns out to be true. And also pre-images, just like in set, are order preserving and mean preserving. We also have images in set, in addition to the pre-images. And in sets, I mean, functions have an important factorization property. You can factorize them uniquely to their codomain restriction version and then embedding. And we will use this same construction to define an image in an abstract category. This optimal, the uniqueness is an optimality condition, just like in the limits. And this optimal factor is defined to be the image of a function in set, and we will define it just like in the same way in an abstract category. And the image of a function is defined, and the image of a subset of from the domain of F through F is just the image of the composition. And in the context of logic, this is represented by the there exists F symbol. And actually, there exists F function between sub objects is a left adjoint for the pre-image. So this is an example of the fact that adjoints arise everywhere. And we can, to reveal this connection with the there exists symbol, we can write there exists F in this form. I mean, why this is important? Because in the first order languages section, we will try to give an interpretation to the there exists symbol, and we will use this there exists F construction there. And the exact same idea, as we said, can be generalized to any categories. And using the optimal factorization idea, and in the same way, we can define the there exists F function in any category. Of course, the category should have certain properties like pullbacks and existence of images. And actually, if your category satisfies these conditions, it's called a regular category. Now, let's look at what a first-order language is. A first-order language is, we all, as mathematicians, we all have familiar with it. It's a language to talk about elements themselves, but not collection of things. Higher-order languages also exist, but they most often lack certain theorems that make first-order languages more amenable to study. A first-order language is just following data. You have some set of sorts. You can think of different types of elements. And you have function symbols between different sorts. And you have relation symbols accepting as input different sorts. And of course, we have also a supply of variables. But we will take a liberal approach there. Whenever we need a new variable symbol, it will be there. And using variable and function symbols, by composing them together, we can create terms. For example, a variable is a term on itself, and if you have terms and a function symbol, you can compose them and get a new term. And also, we can, using logical symbols and relation symbols, we can combine them together to create more general formulas. For example, this is just a relation. If you have terms, you can put it in a relation symbol. You can form equality. We will also have a truth symbol and conjunction, and there exists construction. But this fragment of first-order logic is called regular logic. I mean, in the general first-order logic, you also have conjunction for all quantifiers, but we will omit that for simplicity. We will omit that. For simplicity here. This regular logic is why its name is regular, because it's the internal language of regular categories. In the literature also we have some notations. I mean, we will, if we have multiple sorts, we will denote them as vector symbols, and if we have multiple terms, we will also denote them in a similar fashion. If also we will want to substitute terms into variables and we denote them using these notations. And when you study first order logic, I mean, you have a language and then you have also sequence, and these sequence are formal objects of the form psi entails phi, and phi and psi are formulas. You should, in your mind, read that for all x, psi implies phi, basically. This is the abstraction of that idea. And a theory is just a collection of this kind of sequence. And there are a lot of examples of first order theories in mathematics, for example, group theory, the theory of cosets, totally ordered sets, and even the theory of categories can be expressed in a first order language. And the categorical logic is the semantic side of this first order business. Semantics is the process of giving meanings to symbols. And traditionally, when you give meanings symbols using sets, but in categorical logic, you have an abstract category and you give meaning using morphisms, objects, sub-objects. For example, each sort corresponds to an object, like a set. And each variable symbol, you can think of it as an identity morphism between these sorts. And function symbols are morphisms between these sorts. And relation symbols are interpreted as sub-objects of their input sorts. Just like in the traditional way we interpret formulas and regular and relation symbols as subsets of sets, now we interpret them as sub-objects. And note that in order for this definition to make sense, we need finite products, and also we will also need stability under pullback. So the assumptions of a regular category is really needed for this interpretation to make sense. Also, if we define the symbols, we can extend this interpretation to terms. I mean, using actually intuitive mechanisms. If you just, for example, you have already interpreted terms and you have an interpretation for a function symbol, you can just compose them, just like a function composition, to get the interpretation of the bigger term. And we can define, we can prove using these interpretations substitution, how substitution works. Basically, the interpretation of a term defines the interpretation of its substitution. So, and you can see it as a verification that our interpretation makes sense, because this is the way it turns out in the traditional way. We can also interpret the formulas using our symbols interpretations. For example, you can interpret RT using a pullback, just like in the set we defined it as kind of a pre-image over the function T. And then we can interpret equality using equalizers. Remember that equalizers gives us the agreement set in the category set. So this is like the agreement sub-object of these two terms. And also we can interpret truth as a maximum sub-object, and we can interpret and as a meet of sub-objects, just like in the traditional way it is interpreted as an intersection. And we also need to interpret the existential quantifier, and it is there we use the there exist F construction. And together with the stability under pullbacks, as I said, this is the interpretability of this of the regular logic is precisely correspond to the regular categories. And we have a identical analogous theorem for substitutions of formulas. And another point is validity. In mathematical logic, we have two kinds of validity: semantic validity and syntactic validity. You can think of semantic validity as the truth of a sequence, and syntactic validity as the provability of a sequence. In categorical logic, this is the part it is a little bit of different. We give semantic validity as like this. For example, if we have an interpretation f by m of our regular logic, we say that this kind of sequence is true if the subobject represented by psi is less than or equal to than that of phi, just like in Z actually. It's like a subset. And a theory is just a interpretation that makes all the sequence in T is true. And if T is a theory and sigma is a sequence, we say that T semantically entails sigma if every module of T is also a module of sigma. These are actually standard definitions in mathematical logic. And we have also the syntactic side of it. Syntactic validity is usually defined using some finite list of rules. So if you start from the sequence in T, and if you can prove the sigma using this rule, you say that T syntactically entails sigma. And I mean, the rules are actually pretty intuitive, so I won't get into detail of them. For example, transitivity or P entails P kinds of things. Logical rules to give me the intuitive idea we understand from the AND symbol. Rules for equality. And the holy grail of every logic, I mean, is proving a statement like syntactic validity if and only if semantic validity. And the left to right part is soundness, and the right to left part is called completeness. And this categorical logic and the sequence calculation rules are sound in the sense that if you can prove a sigma from a theory T, and T is also semantically entails sigma. I mean, this you can see also as a sanity check. So if you can prove something, it should be true. And this says that this is indeed the case in the case of categorical logic. And we have also internal logic concept. And it's a kind of inverse process. If you start with the category C, you can build a semantic signature from it. Just take the objects as sorts, morphisms as function symbols, subobject as relations, and you have a signature. And this have an obvious interpretation. And the point of internal logic is that you can reason about categorical statements using this first order logic business. So for example, H is equal to G, F is equivalent to the entailment of a first order formula. And a generic model of a theory is that, I mean, if you have a theory T, you can construct a model. The property of that model is that it captures this theory and nothing else. And you can use this theory RT to prove the completeness theorem. I mean, the details of the RT are as follows. Objects are equivalence classes of pairs of formulas, and formulas and morphisms are provably functional formulas over objects, and composition of morphism is the usual composition of relations. And you can prove that RT is a really regular category, and you can prove that if RT semantically entails something, then T syntactically entails it, and this gives you a completeness theorem actually. And thank you for listening, and if you are curious, these are my references.